Okay, good morning. So today we're going to talk about Goldstone's theorem and the Higgs mechanism, which we talked about last time in a toy model, but we're going to do it today in generality, or at least I'm going to tell you the results of it in generality. So this is Goldstone's theorem and Higgs mechanism. In general. So the general version of this says, suppose we have some complex scalar fields. I'll call them phi sub x, phi sub I of x. I labels which scalar field you're talking about. So these are scalars in some representation. We don't have to be too specific, of a global symmetry. The global symmetry we can promote later to a local symmetry, but for now it's global, and it has matrices Ta, Ij. So A labels the different symmetries, and the indices I and J are running over the scalars that are transforming under the symmetry. Okay, and now we assume that there's some potential for these scalar fields and their complex conjugates. And we're just going to suppose that this potential has a minimum with some of them not equal to 0. So suppose has a minimum with some, maybe all, of these scalars at the minimum not equal to 0. So in the quantum mechanical theory, the statement is that the vacuum expectation value of those scalars will be equal to some VEV V conventionally divided by square root of 2, and it carries an index I because there could be a different vacuum expectation value for each scalar field. So in that situation, some of the symmetries are going to be broken and some are going to be unbroken. Some symmetries, labeled again by A, the index A running over the list of the possible symmetries, are unbroken. And the way you know that it's unbroken is if you take the matrix TA and you act on the vector in field space of possible VEVs. If that's 0, then that's a way of saying that your vacuum expectation value does not transform under the symmetry, and therefore it's unbroken. And some are broken, which just means that if you act with the matrix TA, that's not 0. Okay, so you have to know what the symmetry matrices are, and you have to know what the vacuum expectation values are. So now what you can use is to evaluate this. If this is true, then you call that a broken generator. And for each broken generator, TA, there is going to be a massless Nambu-Goldstone boson, which I'll just abbreviate as NG boson or Goldstone boson. So in what we did last time, for a U1 symmetry, there is only one A. There's only one broken generator. And so we, in fact, found that there was one Nambu-Goldstone boson, which we called G. But in general, there can be more than one. The other thing is, if it's a global symmetry, it may not be an exact symmetry. It might be just an approximate symmetry. And in that case, the terminology that's used is that you say it's a pseudo Nambu-Goldstone boson. And a pseudo Nambu-Goldstone boson is not massless, but it's light compared to whatever other mass scales there are in your problem, right? So if in the limit in which the symmetry became exact rather than approximate, the mass would go to 0. And so by continuity, you expect that if it's just an approximate global symmetry, which is close to being exact, then it will be light instead of massless. Now, if the broken symmetry is promoted to local, which one way to do that is if it's gauged, meaning it has a gauge boson associated with it, a vector boson. So if it's local, which for us is always going to mean gauged, then the would-be Nambu-Goldstone boson disappears. Instead of being massless, it's just gone. And the corresponding vector boson gets replaced by a massive vector boson. Okay, and in fact, you can compute the mass of the vector boson because the Lagrangian contains terms that look like this: G squared VI TA TB IJ VJ times VA mu VB mu. So first of all, where this comes from is from the covariant derivative of the scalar. Okay, the covariant derivative has the vector fields A in it. It also has the scalars themselves, which turn into vacuum expectation values. And then A's just get replaced by V's. That's what happened here. And these generators appear in the vacuum expectation value. So in any case, now you can look at this term and just read off that the coefficient of the term quadratic in the capital V's must be 1/2 times a mass squared matrix okay, which has indices A and B. And so if you want to know what the masses of VA and VB are, you need to do a change of basis in order to make this diagonal. Okay, so we can call this thing, we can call this thing MAB squared, and it has to be diagonalized in general. But once you diagonalize it, then you know what the masses are of your vector fields. Okay, so I haven't proved this, but it's the same idea as we did last time for the U1 case. One thing we could ask is, can other things besides scalars do this? So can other fields besides scalars get vevs? And so one thing you could ask is, well, maybe a fermion could get a vev. So you could ask, if I have a fermion field, can that be non-zero? And the answer is no, because that would break Lorentz invariance, because the fermion has an index that transforms non-trivially under Lorentz transformations. And for the same reason, if I wanted to maybe have a vacuum expectation value for a vector field, that would also not work. Both of these would break Lorentz invariance. So maybe more precisely, you could say that could happen perhaps, but then we should be finding in experiments, we should be finding violations of Lorentz invariance for which there's no evidence at all. However, this can happen. You can have a vacuum expectation value for something like psi bar psi, because psi bar psi is a Lorentz scalar. It doesn't transform under Lorentz transformations, and so this can be non-zero. And in fact, this does happen in quantum chromodynamics. In fact, for the up and down and strange quarks in QCD, if you compute 0 up bar up, that's approximately equal to the same thing for the downs, the down quarks, and not quite as good an approximation, but also it's approximately true for the stranges. And if you ask what that vacuum expectation value is, it's a dimensional full quantity. It's got units of mass cubed, because fermion fields have units of mass to the 3/2. So this should be very roughly of order lambda QCD, the scale at which the QCD coupling blows up, cubed, because that's the only mass scale in the problem. Remember, lambda QCD, very roughly speaking, is of order 300 MeV. Okay, and so that does in fact occur. And this is known as chiral symmetry breaking. This is a little bit off the topic of the Higgs mechanism for symmetry breaking, but I did want to mention it because you could say, well, if we have non-zero vacuum expectation values that are breaking the symmetry in QCD, there ought to be pseudo Nambu-Goldstone bosons. And in fact, there are. So the pseudo Nambu-Goldstone bosons for this broken symmetry, these non-zero vevs, are in fact the kaons and the pions. So pi plus minus pi 0 and the kaons. So this is not an exact symmetry that we're breaking. It's not a gauged symmetry. One reason it's not an exact symmetry is because up and down quarks have different masses, so they're not exactly equivalent to each other. Okay, so they're not exactly massless. Okay, and that's the reason for the pseudo part of the name. But as I mentioned earlier, they should be very light. And in fact, if you think about it, they are, because the mass of the pion squared over, say, the mass of the proton squared turns out to be about 2%. Notice it's the mass squared that really matters. This is a very small number. And so one way of understanding why pions are so light compared to protons is because they are the pseudo Nambu-Goldstone bosons of this symmetry breaking given here. Okay, and in fact, this is, so the pions are massless or very light, but the protons, this is how they get their mass. This is responsible for most of the mass of everything other than pions and kaons. So of the proton and the neutron, etc. Okay, and the Higgs boson and the Higgs field has actually very little to do with the mass of the proton. Okay, any questions on that so far? All right, so let's switch gears a little bit. And we had this a little aside going into chiral symmetry breaking. And now let's talk about the standard model and its gauged local symmetries. So first of all, the gauge group of the standard model is SU3 for color and SU2 for left-handed fermions, and then another U1, which is called U1Y, or weak hypercharge. There's something else called ordinary hypercharge, which is actually not talked about much anymore. The SU2 left is called weak isospin, as opposed to ordinary isospin, which is a global symmetry. And SU3, of course, is color. Okay, and now you can count the number of generators for each of these. So for color, it's 8. There's 1 for each gluon. For SU2, it's 3, because there are 3 different generators for SU2. And for weak hypercharge, it's 1, because there's only 1 generator for, it's basically the phase. Now, what's going to happen, and we'll talk about Friday on exactly how it happens. In today's lecture, I'm just going to be saying it does happen, is that this spontaneously breaks, as we've discussed. The SU2 cross U1 spontaneously breaks to a different U1, which is electromagnetism, which has 1 generator. So we started with 4 generators and we ended with 1 generator, which means there are 3 broken generators, which means there should be 3 would-be Goldstone bosons, which get eaten by corresponding vectors. And so we get 3 massive vectors. And those 3 massive vectors are the W plus, the W minus, and the Z boson. Okay, and the SU3 part of this, we don't actually have to talk about too much because it's not spontaneously broken. We've already talked about QCD, and we know the coupling for this is what we call G3, but there's no spontaneous symmetry breaking. For SU2 left, the coupling is traditionally called G. Okay, and remember the left-handed leptons and quarks are doublets under this symmetry. So they can be arranged in doublet form like this. There's the electron neutrino and the electron, the muon neutrino and the left-handed muon, the tau neutrino and the left-handed tau, the up quark left-handed and the down quark left-handed. There's the charm left and the strange left, they form a doublet, and the top left and the bottom left, they form a doublet. Okay, so those things all transform as doublets, and the right-handed leptons and quarks are singlets, which means they don't transform at all under this symmetry. Okay, so that includes E right, mu right, tau right, upright, etc. And then there's the U1 weak hypercharge, the coupling for that is traditionally called G prime. And the weak hypercharge is Y. Y is just the name given to these charges. These are different for all the different quarks and leptons. And so we can summarize all this information about the symmetries by writing down the fermion representations. And so the way we're going to do it is first write the color, then the SU2 left, and then finally the weak hypercharge. Okay, so for nu E left, for example, that transforms as a singlet of color, a doublet of left-handed weak isospin, and it's got Y charge minus 1/2. So these values, I'm just sort of picking up. These are experimentally determined, of course. Okay, and then the same for the muon and the tau. For E right, that's a singlet under color. It's also a singlet under weak isospin, and it has weak hypercharge minus 1. Okay, and then for up left and down left, they're in a doublet, so I have to keep them together. They're a 3 of color, a triplet of color. They are a doublet under weak isospin, and their weak hypercharge happens to be 1/6. Okay, that's just an experimental value. Then there's U right, which is a triplet under color, a singlet under weak isospin, and has weak hypercharge 2/3. And for down right, it's the same, except that the weak hypercharge is minus 1/3. Okay, so if you're specifying the theory, if you're inventing the theory, you're just picking representations for each fermion, and those are the things that we choose for the standard model. And then for each one of these, there are 3 generations of fermions that repeat the same structure. All right, so now we can write down the Yang-Mills part of the Lagrangian. That is the part of the Lagrangian that has to do with the vector fields. Okay, so I'll write Lagrangian equals minus 1/4. This is going to be just like QED, except it's going to be for the weak hypercharge. And so for reasons I don't really remember, it's traditional to call this B instead of F. Okay, so B mu nu is the field strength, just like F mu nu in QED, but this is for the weak hypercharge gauge group. Okay, and then there's a 1/4 for the SU2 left, which has an index A that runs from 1 to 3. Okay, so this is for SU2 left, A equals 1, 2, 3. And then for the gluons, which aren't going to be involved in spontaneous symmetry breaking directly. Okay, and so this is GA mu nu is for SU3 color, and A runs from 1 up to 8. Okay, so to be more specific about what these field strengths are, B mu nu is partial mu B nu. There, the B with a single index is the analog in quantum electrodynamics of the vector potential, A mu. And this is antisymmetric. And oops, I should have written B there, not A. Okay, and there's no extra part of this because the structure constants are 0 for AU1, just like in quantum electrodynamics. But for the W's, they look very similar. Again, I'm using the same symbol for the field strength and the vector potential with one less index. Okay, but now there's an extra term which looks like this. And that reflects the fact that the structure constants for SU2 are nothing other than the antisymmetric tensor epsilon. This is the structure constants for SU2. Okay, so now in terms of these, we can write down the interactions of fermions with the vector fields, which comes entirely from the covariant derivative. So interactions of fermions from covariant derivatives. Okay, and so let me just write down the covariant derivative part that's going to be plugged into the Lagrangian. I have a covariant derivative acting, for example, on a doublet of left-handed leptons. And this is going to be equal to the ordinary derivative, which isn't going to give an interaction. That's going to give the propagator part. Okay, plus Ig prime B mu times the weak hypercharge for these fields, which I'm going to call Y sub L plus Ig WA mu TA. Those are the proportional to the Pauli matrices. So 2 by 2 Pauli. All of this acting again on the same doublet. So the only part of this that mixes up the doublet terms is this last term, because it has the Pauli matrices. The rest of this is proportional, to the identity matrix. Okay, and so here a 2 by 2 identity is implied. Okay, and so that's how the covariant derivative acts on these things. And when I plug this into the Lagrangian, now I'm going to have an interaction between fermions and vector bosons. Okay, just to see how it works for the right-handed electrons, they're not doublets. And so I can just write a covariant derivative as partial mu plus Ig prime B mu Y left. Maybe I should have called this Y left, YL left and YL right, acting on E right. This, by the way, is nothing other than, you go up and you look here and you can read off that it's minus 1/2. Okay, so this is minus 1/2 and this is minus 1. So they are specific numbers. The G primes are the couplings. The G and G prime are the couplings. The B mu's and the WA mu's are the vector fields. But then the coupling is determined by these charges, which are always just rational numbers. Okay, so another way you can do this is you can write in the covariant derivative for the left-handed fields, WA mu TA, using the fact that the TAs are just the Pauli matrices, this becomes 1/2 W3 mu W mu1 minus I W2 mu, W1 mu plus I W2 mu, and then minus W3 mu. So this is just a way of writing explicitly out what are the different components of the SU2 left gauge bosons as they appear in the covariant derivative. So we can take it further by now taking these equations and just writing out all the components of the covariant derivative. Let's go ahead and do that just to see what it looks like. So we can write d mu nu e equals partial mu nu e plus I. There's g prime YLL b mu plus g over 2 W3 mu times nu e. That's sort of the identity part of the matrix. And then there's the off diagonal part, which is I g over 2 W mu1 minus I W2 mu. And that's multiplying E left. So you see the covariant derivative for a neutrino has a part proportional to the electron with this combination. And similarly, I can do this for the electron. Okay, so now we get this part proportional to the identity. So it's still E left, but now there's a part proportional to the neutrino field. Oops. And things are simpler for the right-handed electron. That's just partial mu E right minus I G prime B mu E right. So there I've used the fact that the charge of that is just -1. So if we look at this, we see that we have a problem perhaps because it looks like this might be breaking electric charge. This has no charge. This has no charge. The neutrino has no charge. But here the electron has charge -1. So the only way out is if this combination has to have charge +1. Similarly, this has charge -1, the E left. So does this, so does this. But this has charge 0, so the only way out is if this combination has charge -1. Okay, so what we've learned is that electric charge will be conserved implies that the combination W mu, I'm going to write it like this, W mu plus, which is a normalized linear combination. The 1 over square root of 2 is just to get the normalization right. It doesn't matter for this argument, but this has charge +1. And W mu minus, which is the orthogonal linear combination, okay, which is the combination appearing here, that must have charge Q equals -1. Okay, and so now you can put all this together. You can take the covariant derivatives, plug them in where the ordinary derivatives would go in the Lagrangian, and see what you get. I'm going to do this by just writing down that part of the Lagrangian. So what you get is that the Lagrangian contains minus g over square root of 2 nu E bar, gamma mu E left, W mu plus. E left means, of course, P left acting on the full field E. Okay, and then there's minus g over root 2 E left bar gamma mu nu E W mu minus. Which is great because this is nothing other than the charged current weak interaction that we've been talking about when we talked about the weak interactions. For example, if you did the same thing with muons and you put this together, then you describe muon decay. It's in fact the same Lagrangian we've been using. Okay, and also the Lagrangian has these terms in it from the field strength squared. So there's partial mu W plus nu minus partial nu W mu plus times partial mu W minus nu minus partial nu W minus mu. All right, so we've got basically, this gives us the propagation of the W field along with its mass, gives us the Fermi-Lagrangian that we talked about with muon decay, for example. Going along with this, B mu and W3 mu both have zero charge. So the fact that they both have zero charge and they're both vectors means that in general, they might mix with each other. In other words, one could turn into the other. And in fact, they do. So let's just allow for that possibility and see what happens. So they mix, and that means that fields with well-defined masses, meaning mass eigenvalues, are linear combinations of B mu and W3 mu instead of being them themselves. Just on general principles, because it could happen, we might expect that it does happen. And it turns out it does. So let's write down what that means. That means we have some matrix of fields, which is a linear combination, that's a matrix, times W3 mu B mu. And we're going to call the entries in this matrix cosine theta W minus sine theta W, sine theta W, cosine theta W. So that's an arbitrary orthogonal matrix that does a change of basis on these, which are called the gauge eigenstate basis. And the result we're going to call Z mu and A mu. Okay, so theta W, which we haven't really said what it is, it's just a name. This is the weak mixing angle, otherwise known as the Weinberg angle, okay, or Weinberg. They happen to have the same letter. Okay, and it's an angle in field space, not in real space. All right, so these are going to be the mass eigenstates. And these are the interaction or gauge eigenstates. And we're just acknowledging the fact that they don't have to be the same, because every property of these fields is the same. They have the same charge, they have the same Lorentz structure, and so they should be able to mix. So you can do the inverse of this transformation, of this change of basis, which just says W3 mu B mu, if you invert it, is cosine theta W, sine theta W, minus sine theta W, cosine theta W, times Z mu and A mu. Okay, so A mu is going to be what we know and love as the photon field. And in fact, if you do this transformation and you plug it in, you find out that it has exactly the Lagrangian part of it is exactly the same as for QED. Whereas Z mu is going to be the Z boson field, which is going to be massive. A mu is going to be exactly massless. The reason you can think of why is it exactly massless, it's the linear combination that does not eat a would-be Goldstone boson, whereas Z mu does eat a mass would-be Goldstone boson. And so the thing that eats a would-be Goldstone boson gets a mass. Okay. So we're going to actually understand that next time, basically, is when we'll figure out how that exactly works. But for now, I'm just asking you to believe that it does work. And now let's think about, in terms of these fields, what are the interactions of the fermions that come from these covariant derivatives? And it's specifically really from these parts, because those are the parts that involve B and W3. All right. So what we're going to do is we're going to require that the photon couples correctly to these particles. So for example, if I have d mu E right, let's write this out again. Now what I'm doing is I'm writing it in terms of A mu and Z mu instead of B mu and W3 mu. Okay, and then there's, right? So when I write it this way, I've written it in terms of the photon coupling to the right-handed electron. And so this G prime cosine theta, this must be what we called in QED the coupling E. In QED. Otherwise, QED wouldn't work, and QED is a very, very well-tested theory. Okay, so what we know is that G prime times cosine theta W must be equal to E. Now let's do the same thing for the left-handed electron. So also d mu E left equals partial mu E left plus I times, I'm just rewriting what we had before, but I'm only going to worry about this time the part of it that has an A mu in it. Okay, and so now this stuff here must again be minus E. Okay, and so what we learn is from this is 1/2 G prime cosine theta weak plus G sine theta weak is equal to E. But we already know G prime cosine theta weak is equal to E. And so this tells us that G times sine theta weak has to be E. Okay, so we've derived two equations that relate the standard model Lagrangian to the QED Lagrangian by matching the weak mixing angle and the two couplings in the standard model theory to the one coupling that exists in the QED theory. So as a check, maybe we should do the neutrino too. So also, we can look at d mu acting on the neutrino state. So let's see what its coupling to the photon is. So this time the terms in the covariant derivative look like this. I'm just writing down the part of it, again, that has a mu in it, because that's the photon field. We can worry about the Z boson part next time. But now this coefficient, all of this stuff must be zero, because neutrinos don't couple to photons. So this must equal zero exactly. Neutrino has no photon interactions. It doesn't know about the photon at all. Okay, and so if we write down what that means G prime cosine theta weak has to equal G times sine theta weak, which fortunately is consistent with the previous two boxed equations. So that's just a check. It's a very good thing. It shows that, in fact, the neutrino does not couple to photons, just as we already know. Okay, so now we can summarize what we've learned about this relationship, and there's different ways of writing things. So we can rewrite the above as, first of all, if I take the ratio of the two boxes, that tells us that the tangent of the weak mixing angle is just the ratio of the U1 weak hypercharge coupling to the weak isospin coupling. Okay, then we can take the equations in the boxes and add them together. Okay, and we get E is equal to, if you solve for E, you get G times G prime over the square root of G squared plus G prime squared. So that's very useful. It tells you that you can't just pick anything for G and G prime. You have to pick them in such a way that you get out the measured value of E, which, remember, is very well determined by the fine structure constant, because E squared over 4 pi is 1 over 137.036 something, something, something. So other things you can do with that is now you can solve for example, sine theta W. That's G prime over square root of G squared plus G prime squared. And cosine theta W is G over the square root of G squared plus G prime squared. So in other words, if you pick your high energy, or you pick your standard model couplings G and G prime, that determines the weak mixing angle, and it determines the QED coupling. Right, so there are these relations. So you can now appeal to experiment to figure out what they have to be. Here are the numerical values of these various things. And again, this depends a little bit on how you do renormalization. So these are, in parentheses, I will say renormalized couplings in a particular version of renormalization called the MS bar scheme. That has to do with dimensional regularization. And you have to pick a renormalization scale, and it's traditional to pick the Z boson mass. The reason for choosing that is the Z boson mass is nice and high, so you don't get large effects sneaking in from loops with QCD that are too hard to handle. And it's very well known. This is 91.19, actually it's known more accurately than that, GeV. So with that, G turns out to be about 0.652. G prime is 0.357. E is, I'm just going to write down the first few digits, even though it's known much more accurately than this, 0.313. And sine squared theta weak. For some reason, it's traditional to write it as sine squared theta weak rather than theta weak. It's about 0.231. Okay, and so one thing you learn from this is that SU2 left is stronger than the U1 weak hypercharge. All right, one more thing is that you can now, we did this for the electron and the neutrino here, but you could do the same thing for the quarks, and you find out that everything is consistent as it has to be. And in general, you find out that the electric charge for a fermion is equal to the third component of weak isospin plus the weak hypercharge. Okay, so this is electric charge. This T3F is +1/2 or -1/2 for left-handed fermions, depending on whether it's the upper or lower component of the doublet. And it's 0 for right-handed fermions. And this Y sub F is the weak hypercharge. I should mention that some people have a different normalization. About half the people would use a different normalization for weak hypercharge, so there's an extra factor of 1/2 in that formula. But up to that convention, this is true for every fermion. We just enforced that it was true for the electron and the neutrino, but it's also true for up quarks and down quarks. And in fact, we haven't introduced the Higgs field yet, but it's also true for the Higgs field. Okay, so we're out of time for today, but next time I'll mention first what happens with the Z boson, what its couplings look like, which you actually get to work with on a homework problem. And then we'll complete the standard model part of this by talking about the Higgs mechanism and how it actually makes this spontaneous symmetry breaking work. So today I just assumed that it worked, but next time we'll see how the Higgs actually does make it work. All right. Oh, and a reminder that the last class on Friday will be face-to-face again. Just one last time to get back to face-to-face before the semester ends. All right, any questions? All right, if not, I will see you in person on Friday.
Thanks.
Thanks, have a good one.